So welcome to this very important lecture in perspective of trying to prove your methods which you have developed to know, and this is called as systematic evaluation and validation. So this is a place where we are going to learn about how you are going to benchmark your algorithms, which means to say as to how good is your method performing as compared to other methods. So if you are looking in perspective of developing something new, if you're looking in perspective of actually trying out what somebody else has worked out already on, then this is a particular chapter you will need to understand in order to evaluate if there are 7 different methods available to solve one single problem, then which of these methods is most suited to solve your problem and what are the trade-offs you can always achieve. So maybe you can make it faster, compromising certain part on performance, or maybe the other way around, that you don't want it to be faster, you have enough of time to spare on it, but you actually want it to be the most accurate as much as possible. So we will be discussing about them one by one. The way this lecture is actually organized is I would be initially speaking about what is as per definition a data set and what are baselines. Then I would be telling you about retrospective versus prospective experiments and what they mean. We will also be discussing about the bias variance problem and the bias variance trade-off, which we often speak about in some kind of a pattern recognition, machine learning or computer vision task, and what the perspective means for medical image analysis as well. Then we will be speaking about the sample sufficiency issues and when do you call something as a sufficient sample. Following that, we would be entering into certain very standard evaluation methodologies. The first one will be for evaluating segmentation algorithms and segmentation performances. Following that, we would be entering into classification evaluation. So classification evaluation can also be used for segmentation problems if you're looking at segmentation as a pixel wise classification problem. Otherwise, you can also be taking them as image level classification problems or volume level classification problems or even case level classification problems. From there, we enter into a very standard way of evaluating your performances of algorithms in any kind of a learning based task, and that's called as receiver operating characteristics. So once we have all of this ready, that you know about what data sets are, what your baselines are, where your methods are standing with respect to others in terms of a very standardized experiment, the major thing which comes down now is you need to cross validate, and we will be learning about how to do a folded cross validation, which basically means that can you keep a part of your data as blinded and not use it during training and see how the performance comes, and now can you actually do it repetitively or iteratively over a cycle of procedures so that you know what is the best case performance, worst case performance and average performance of your algorithm when it's actually put into a field level deployment. So let's get started. The first one is about data sets and baselines. Now, as I put this one is it can very categorically be said as a playground and all the prior record holders. Now imagine any of your algorithm development task is actually a one single player game. It's no more a team player game. Even if it's a team player game, then we would rather call this as a World Cup of some sort of a team playing games over there. Otherwise, still consider this to be an Olympics of single events. Now over there, your playground is basically where you are going to play the game you are going to do. So obviously you are not going to do some sort of a pole vault in a swimming pool. That's quite out of way. So you need to understand as to what's your playground, and that's called the data set where we are going to work on. On the similar way, if you are actually somebody who is competing to be the best swimmer, you are not going to look into timing performances across pole vaulters or across javelin throwers. So that's the point where you need to understand as to what baselines are which you are going to use. Now let's get into the first part of it, which is your playground or the data set. Now if you look into the data set part over there, then we have very standard paradigms of evaluation. So if you look into the dataset part over here, we have very standard paradigms of evaluation. The first and foremost thing to be guaranteed for medical experiments is that the data needs to be anonymized. You cannot compromise on leaking out the patient information at any point of time. Now information is obviously the name or some entity by which the particular subject whose data you are using can be identified. For all practical purposes of research and for all ethical concerns, we cannot divulge out the patient information in any way. And for that particular reason, you would see that most of the data sets which are publicly available, they will never divulge out this information. The patient field is always kept as blank. The only thing you might ever get is basically the age of the patient, which is actually a clinical identifier, the gender of the patient, which is again a clinical identifier, and sometimes you would be getting down extra information like the race of the patient, the kind of economic background they come from, the education background of the patient, the kind of jobs they are doing. So these are extra metadata which play a lot of significant part in terms of developing some sort of a medical diagnostic system. The next one is that you need to choose the same set of modalities or the same modality. So if I am trying to do an experiment in which I want to segment out, say, the left ventricle of the heart. Now I cannot say that I will be segmenting left ventricle of the heart and trying to prove its performance using 5 images of ultrasound, 7 images from MR in T1, 3 images from MR in T2, and say 8 images from a CT angiography system. Now this is way wrong. You need to be either focusing on one of the modalities, or say if you are doing a multimodal, then for all of your patients, if we say you have about 35 patients over there, on which so for our purposes we will call them as subjects, because we don't know whether they are actually patients or not, they might be healthy individuals as well. So if you have 35 subjects as well, you should be having all of the modalities for all of them, the same set of modalities, or maybe the only modality on all of them. This is how you need to prove, and you need to be very cautious about that. You cannot compare apples and oranges, so you cannot compare performances of segmentation on ultrasound with performance of segmentation on CT images. The next one is that you need to have a cohort from where you are going to collect all the data, and this cohort means that you need to have similar set of diseases. So if you are trying to quantify certain cardiovascular diseases, then you will need to necessarily know that all of these subjects, they come with a prior history of cardiovascular problems, or they are perfectly normal as far as cardiovascular problems are concerned. But then if you want to look at segmentation for certain disease indicators, or you are segmenting a particular lesion of the brain, and all the subjects which you are getting down over here on your MR scan of the brain on which you want to segment a lesion never had any sort of a brain problem, or that never had a problem in terms where a lesion would form in the brain, then your cohort is actually flawed. You cannot use that data for doing over there. The next one is that they need to come down from a similar genetic makeup. Now all of us by now in this global age, we do understand that genetic makeup plays a very significant role in how our bodies are formed, how tall we are, how wide we are, what is our weights and everything. In fact, the size of the skull, the shape of the skull, in which the whole brain is also encapsulated, varies from different genetic groups to different genetic groups. So you need to be very cautious about using a cohort from a single genetic makeup, or even if you're doing it from say 3 different genetic makeups. So let's consider that you're taking the Indian genetic makeup, you're taking an African genetic, Southern African genetic makeup, and you are again taking a European genetic makeup. Then be very sure that you are actually going to take equal proportion of people from all of them, and they should also be balanced in terms of the number of the proportion of genders. So you cannot take all females from the Indian population and all males from the African population and then try to come up with a disease cohort summary. So you need to have both males and females. If it is spread over a span of age group, which means that this disease can exist from 10-year-old to 100-year-old, then you should be having representative population on each of them. So you cannot say that my Indian population just has people from 10-year-old to 40 years old, and my African population has all people from 50 years old to 100 years old, and now I want to compare whether the effect, and you cannot generalize and say that with whatever findings you are getting down on the 50 years old to 100 years old on the African population, you cannot bring the same thing and say for the Indian population of 50 years old to 100 years old, because for the Indian population you just had for the group of 10 years old to 40 years old. Now this is what you need to keep in mind. The next part is that the demography also has to be kept in concern. So these are major things you need to know when you are planning a cohort. For most of the publicly available data sets, these are actually sorted out, because when data collection goes through an institutional regulatory approval, this complete experiment design of how the data will be collected and how it will be annotated and stored is actually reviewed much before the data collection starts, and even after the data collection, before the data is actually released for public use, and said to satisfy a certain quality based on which algorithms can be evaluated. It's again internally audited in order to check and verify whether everything which was promised and was expected by the committee for regulatory approvals has been satisfied before the data is released out. The next part is that you need to have equal number of subjects per pathological group, which means that basically if you are looking for a certain sort of cancerous lesion. Now cancers can be of different categories. There can be type 0, which is basically where no cancer has been found, to a type 1 where it is not yet a cancer, it's some sort of a tumor but in a benign form and most and least likely to ever become a cancer. Then there can be type 2, which is it is exhibiting some sort of a growth, but that is not exactly a cancer. Then there is type 3, which is a borderline case, which means that it was sort of type 2 maybe a few instances of time ago, which is a few days ago or a few weeks ago, but now it's sort of showing a progressing behavior towards type 4, which is a borderline case for a start of a cancer, and maybe till type 5, which is a case where you definitely have a malignancy proven down, and type 6 where it's actually infiltrating out and going to infect other organs as well and is the most critical case. Now if you are looking at each of these classes, it's expected that you have data for each of these classes. Now you cannot say you don't have data for type 0, it's okay, because normal people who don't have cancers might not turn up for it, okay. But if you don't have data for type 1, you don't have data for type 2, you cannot generalize your algorithm's performance for type 1 and type 2. You will always be reporting that you are able to only validate performance for type 3 and type 4, type 5 lesions for which you have your images available to you. So this is one thing you have to keep in mind. You cannot say that I have a universal lesion segmentation algorithm of some sort when you don't even have data sets from type 1 and type 2 available to you. So this is another major concern to be kept in mind. Although in medical images we do understand that getting normal is a problem, and that's always kept inside the reservation, saying that without normals, just for the disease categories, we are definitely able to prove it. Now the other part is that if you have access to a follow-up data or prognosis data for your complete cohort, use it only in that case. Suppose you don't have follow-up data for all of your subjects enrolled in the study, or all the subjects from whose data you are using, in that case do not use it. So follow-up basically means that the subject came in for the first time, you got a certain sort of a diagnosis, you have the imaging data and everything available to you, you're doing your segmentations and everything. Now the subject comes down for the second time, you cannot consider this to be a second case anymore. This is actually a follow-up of the first case itself. So your sample size is not increasing over here. Basically your temporal sampling of the observations are increasing. So your number of observations is more, but number of samples is not more. This is what you need to keep in mind. And use a follow-up only if you have follow-up available for all the or a significant sizable portion of your population. Say you have some 80 subjects and you have 2 different classes, so 40 subjects per class. Now for the first class you never have a follow-up, and for the second class you just have keep on having follow-up. Now if you want to report follow-up, you need to very categorically say that I am reporting follow-up only for this category 2 of subjects for whom follow-up was recommended, and out of these 40 subjects over there, maybe I am reporting only for 30 who actually turned up for follow-up, and this is the observations on the differential side of it. So this is how reporting has to be very crisp and clear when you are mentioning it at some point of time. Now from there we move on to as to what is about the prior record holders and what we would mean to say in terms of what records we need to break. So over there you would clearly look that you will be getting about the prior record holders from your literature reviews. So in these literature reviews are basically all the previous methods, all the previous papers which were reporting something which is related to the work over there. Now in case you see that those methods were reporting on some other data set or their own data set which is not publicly available, then it's generally suggested that you re-implement that method on your standard data set and report it, because 2 different data sets and reporting performance on them and trying to compare is basically a farce over here. Because what you are trying to in effect do is that, say I am in terms of cricket, let's do it something that I'm trying to prove team A's capability of playing a 2020 match to team B's capability of playing a test series. Now that's way wrong, because everything has a different game plan, everybody has a different game span over which they are doing. Somebody might be a good sprinter performer on a shorter period of time, somebody might be somebody who can play on for a longer period of time. Now this is a wrong way of proving. Instead of that, if you really want to compare team A and team B in playing 2020, you need to make both of them play 2020. Or if you want to make each of them find out their performance on a test, then play one against the other on a test match itself. You are not going to compare one team for playing 2020 to the other team for playing a test match. Now this is what you need to keep in mind over here, that you need to re-implement the method and use it over here. Most likely you would be getting an open source implementation for the algorithms, which makes it much more easier. Now from there, you would also need to specify if you are using the same set of metrics for evaluation. So if you're using accuracy for benchmarking everything, use accuracy. Don't just branch off at some point of time, say that algorithm B and C and D have reported sensitivity, so we are just going to report sensitivity and compare them. So that's also a wrong way of doing it. We come down to what they mean and how they will be impacting your total performances over there. Including that, always mention about what is the performance and what was the time taken down. Because in this particular field, we are very cautious about how much of time you are consuming in order to do a certain experiment and how you would be validating that. So from there, we come down to where to get data sets. Now, as I had mentioned on the first lecture itself, is a very good place is actually going down to grandchallenges.org and trying to find out from there what are the existing challenges and if there is something new which has come up over there or not. Beyond that, you also have a lot of public data sets which we would be listing down on the course web as well, so that you can get access, you can have a ready-made lookup access to them as well. Now benchmarking, typically what it would be looking like is something like this. So I have taken down this results from the drive dataset for retinal vessel extraction, and they have a very intuitive method in which what they do is you have the original image, you have a ground truth, and then performances of different methods. So you have small thumbnails over here, and then the accuracy, sensitivity, specificity, accuracy, and area under the ROC curve, which is reported for all of them. And this is a typical way in which benchmarking is done. So this is an image to image base. Now for all the images, if you take it together, then you can consolidate and always give down an average value coming down over the whole data set for this particular one. And all of these are different methods and by the authors who are present over here. So this is a way in which benchmarking is generally expected when you are doing it over a data set, and it's expected that if you're writing on a paper or report someplace or consolidating your own performances, then you report it in similar way over there, that you put down what prior art is, because don't expect that the person who is reading it or evaluating it is an expert or can readily recall what performances were. So you are expected that you put down everything on a single piece of paper so that it becomes very much evident for somebody to track as to whether you are good or how, even if you are bad, then how bad, and is there some sort of a trade-off which you are able to achieve. Now from there, I would be speaking about what experiments are. So typically we have two types of data collections within experiments. One of them is called as a prospective, the other one is called as retrospective. Now in prospective, what you do is, as the name suggests, that you basically plan for the data collection before the event occurs. So this is what's done by pharmaceutical companies for drug trials, and you typically use a controlled animal model for these sort of trials. There are humans who also enroll for similar kind of trials over there, but they are much more serious affairs and come much later after animal trials and all sort of regulatory approvals and ethical clearances. Now here the idea is basically to test a certain sort of hypothesis. So say you are coming up with a hypothesis that given I am injecting certain sort of a drug to a person with this kind of a grade of tumor, then the tumor is going to go down. So there will be animals on whom these same sort of tumors will be created. So say 100 animals on which the tumor is created, and another 100 animals on whom the tumor is not there. And now what they do is they keep on injecting the drug on each of them, and they do a follow-up study. Now on the group of animals on whom the drug has been injected, if there is a hypothesis that the lesion is going to shrink, then you will be observing for the shrinkage in lesion. Now for image analysis, where the job comes in, that the lesion would obviously be imaged by somehow, so maybe a CT or an MR, and your job is basically segment it out and do volume estimations over time and find out. So this is definitely a follow-up experiment which you are going to get done over there. The number of samples cases you have for healthy and the number for the tumor model is always same, so you have a data balance over here completely. And on the other side of it, what you will be looking is that whether the drug is inducing some sort of a side effect or secondary lesions in healthy subjects as well. So this is what you need to keep in mind during evaluations. Now the good thing about this experiment is that you have a class balance, because now you can ensure how many I need for the normal one, how many I need for the abnormal one. The bad thing is that this definitely requires a lot of regulatory approvals, because you are subjecting some living beings onto your experiments and making them scapegoats. So you need to be very, very cautious about that. And next is, obviously they are very costly to perform, because you are keeping everybody informed, and the whole data collection and everything is from your own pockets which goes into it. But obviously this is the basis for doing pharmaceutical trials and how new drugs come into testing and then eventually into market. The next one is a retrospective study, and this is when the data is collected as the event occurs. So one common example is epidemic data. So there is an epidemic breakout of something, and the health officers are constantly recording that data. So they are not planning as to when the epidemic is going to occur, but as it occurred, as there was a surge in the disease, the data is just kept on being collected over there. So this is where you have you will not always have imaging modalities, but in a lot of cases you will be having imaging modality efficacy studies which go over here. So which means that over the long run, so say there is a center or there is a particular machine whose quality is to be evaluated, so whatever scans are being done on the machine, everything is recorded over there, and then people are going to use this at a later point of time in order to evaluate whether the whole study was good or not, or the machine was performing good or not. Now over here what we do is basically we need to form a hypothesis from the observations itself. So here the hypothesis is previously not known, we just observe certain things and then sort of create a model in order to form a hypothesis. Now the good thing about this kind of an experiment is it's obviously less expensive and generally free of cost, because it's just in a treatment protocol when or a diagnosis protocol when the images or data are getting acquired. You are just going to make use of this information for your research. So regulatory approvals are also generally hassle free, because the event has happened, the data has been recorded. You are just going to get a regulatory approval for anonymizing the data and using it for proving down a particular hypothesis, or for basically designing a particular hypothesis by looking at the data. Now the cons is this will have severe class imbalance, and the reason being that, say there is a particular say we again get back to the cancer example from class 0 or type 0 of cancer till type 6 of cancer. Now type 0, most subjects will not be coming down for an imaging study because they don't have a lesion. Type 1, type 2 is what you will be having a lot of patients, and in fact like about 80 to 85% of subjects will be just type 1 and type 2. And on the other side of it, type 6, which is the most crucial one, which you would like to basically be very sensitive to, will have maybe 2 or 3 patients just coming down for those. Now if you look at the relative distribution of each of these classes, it's never balanced. So some classes would be very heavy, some classes would be very low, and there are chances that whatever classifiers or learning engines you are going to develop, they are going to get very much biased towards this particular one which is very high. Now we come down to this issue on the sampling in the next slide, where I would be explaining them in much more detail as to what happens. Now about the sampling issue which I was telling you, now one particular case is which we call as a bias sampling. So let's take just 2 categories of problems. So I have my red squares and red plus symbols, and I have my blue circles over here. Now these and then these green lines are basically my separation margins in a classifier. Now what I wanted to say was, you will be seeing that there are multiple of these separation margins over here, and the reason is that based on how your learning system is initializing itself, that you can get any one of these. So there can be multiple classification margins and separation margins, as we had learned in the previous lectures on simple classifications. Now what happens over there is that as you would be having a biased class, which means that there are more number of samples from blue, and say this is what I said was benign cases or type 1 and type 2, okay, and you have less number of samples from malignant classes. Now the problem which comes over here is that you will be heavily biased towards making a decision in favor of the benign, and you will be mistaken for malignant ones, and that's when this margin shifts a lot far away from here. So anything which comes in these border zones, they are most likely to be made called as benign and less likely to be called as a malignant, okay. Now the other problem is that you also have sort of a variance problem in the second case. In this second case, what happens is that you will see that the number of samples you have for benign and malignant is sort of same, almost same number of samples, but the problem is that they are not quite spread off in this part, which means that there is a lot of gray zone over here. Now if you look at this total feature space, a lot of this space is basically where you never had any samples come on. Now if there are samples coming on from here, you are just basically left at like the mercy of whatever classifier line came down over there, and there is no high surety that you are doing it with a very confident decision. Now this is a problem which happens with the unbiased but a data set which has a low variance, whereas the best one is actually an unbiased and a high variance data set, which means that your data set is quite spread across the whole of feature space, such that you are getting a classification margin which is a unique classification margin, and the chances that it makes error is actually much lower. Now how do you ensure this is a major question. I mean, until possibly you have the classification margin, you can never ensure it, but at the point of data collection, if you can ensure that you have samples from at least one sample from every single manifestation coming down, and you have some sort of a balancing between the number of positive samples and negative samples, you should be able to get down a way in which you can always have a unbiased estimator with a very high variance on your sample sets being created. So this is an issue which you will have to really take care of by yourself. But the problem is that it's not so easy. I mean, it's much easier said than to be done, because sample sufficiency for medical images is actually a myth. It's a serious myth. Now you will have more cases and samples for normal or healthy, or say all the benign cases, and for abnormal diseases, the rarer a disease is, the lesser is the number of samples you will get. And the problem is that you will always need this performance margin to be highest for this rare disease. Now the solution is actually in order to do something called as a data augmentation. Now this is a standard technique used for a long period of time in computer vision practices, and the idea was much more simpler in computer vision, because you have a lot of natural languages, natural scenes which you are using over there, and from these natural scenes you can actually augment it out, synthetically augment out something. But then for medical imaging, you need to be very cautious as to how you are augmenting. Now first and foremost, how you need to do is that you need to replicate samples for the weaker class, okay. So replicating samples are not going to just solve your problem, because what you would be doing is, on the bias variance space, if you look at it, you will still be having a much lower variance. You are not going to increase the variance, you are just compensating for the bias by replicating samples. Now in order to compensate for the variance as well, what you can do is you can introduce some sort of rotation and affine transformations, which is you can do a bit of skewing, scaling, or you can rotate the lesions or image appearances a bit within certain sort of a tolerance limit. So obviously a CT scan of an upright person and a top down person is very different, so you cannot do that much of a 180-degree rotation, but maybe within a 5 degrees or 10 degrees of tolerable limit you can do some amount of rotations over there. But definitely restrict the use of warping or applying intensity transformations, because these are very much disease specific and lesion specific. So by applying a warping, you are basically a lesion which is oval, and you suddenly warped it in a weird way and it becomes jagged in shape, so that's no more a benign lesion in any way, so that becomes very close to a malignant lesion. So this is where you're your augmentation is going to introduce errors into your learning system. The other one is that if you're applying intensity transformations, these are factors of tissue energy interactions that we had studied in the previous lectures. So you are going to again play around and some sort of introduce errors into this tissue energy interaction, which is very specific for diseases and modalities. So you cannot use these ones. Now these are just certain suggestions. There is definitely no defined way of doing it, and these are how we have been able to solve a lot of problems till now. Now from there I come down to very simple metrics. So say that you have a segmentation problem. So this was an object which you had to segment, and this is some sort of a lesion in an MR which you were wanting to segment. Now there is obviously a ground truth which is available. We call this as G, and X is the coordinate location. So the value of Gx is wherever the object is present is 1, and everywhere else it's 0. And this set of all pixels which belong to this object over here is also called as A. Similarly, there is a performance from your algorithm, whatever you are designing, and that's called as the delineated objects A, and we represent in a similar way fx, and the set of these object points marked over there is called as B. Now in order to evaluate segmentation, we have 4 different measures. One of them is called as over segmentation, and this is basically the number of pixels which are segmented, which are said to be belonging to the object as per your segmentation, but actually do not belong to the object. So that's where I do an intersection with the complement of this ground truth. Okay, you are always going to divide it by the number of samples present in the ground truth itself, because that's the normalizing factor in all cases. Under segmentation is the reverse of it, which is, it means that the pixels belong to the object as per the ground truth, but as per your segmentation they do not belong to the object. So you can have an under segmentation performance over there. Your algorithm can have both over segmentation and under segmentations. The next one is called as the dice coefficient, and this is basically twice the intersection of the areas divided by the sum of the areas over there. And the other one is called as a Jaccard coefficient, which looks very similar to a dice coefficient, except for the fact that this is an intersection divided by the union over there. So if you have a perfect segmentation, this would end up being as 1. Now from there, these were all area based segmentation evaluation methods. We come down to another one which is called as a distance based, or when you have contours coming down, then how do you map down whether my contours are very closely located to each other or they are very far out. So to give you a very simple thing is that maybe your object is actually oval in shape, and you found out a flowery like pattern around that oval. So all of your area wise overlap measures would give you a very high segmentation score, but your boundary was not that smooth which you wanted to find out. Now for this you use this kind of a metric which is called as a Hausdorff distance. Now for a Hausdorff distance, what it does is quite simple. So for every point you find out, if every point on your segmented region and every point on your actual ground truth G, you would find out which is the corresponding point over there. So you find out the largest distance of the corresponding points, and then you are just going to take that maximum of the distance, and this is the maximum error in terms of contour deviations which you would be plotting now. Now over here it might appear to be very complicated, but the idea is pretty simple. You just need to find out the centroids for both the objects, and either in a clockwise direction or in an anti-clockwise direction, you just need to do the polar plot over there. Now once you find out the polar plot over there, you have a point-to-point correspondences between the points coming down. Just measure those units over there, and after that you need to find out what is the maximum of that, and that's a clear-cut way of doing it. From there we come into classification measures, and so all of your problems are not exactly segmentation. Somewhere you might be giving an image as the input, and you just want to find out what is the classification result over there. Now for typically a 2-class prediction model, you will have a ground truth on which you have the positive class, which is maybe the disease class, and the negative class, which are all the healthy classes. Now you would be predicting also as positive and negative. Now for some of the samples which are actually positive, you would also be predicting them as positive, and they are called as true positives. Some samples which are actually negative, you would also be predicting them as negative, and that's called as true negative. There would be some samples which are actually negative, but you are predicting them falsely as positives, and they are called as false positives. And there are some samples which are actually positive, but you are falsely predicting them as negative, and they are called as false negatives. So this kind of a matrix is called as a confusion matrix for a 2-class problem. Now if you have a multi-class problem, say 3-class problem, then what you would end up getting is that you can take class 1 as your positive class once and get a confusion matrix, class 2 as your positive class once get the confusion matrix. So class 1 can be misclassified as class 2 or class 3. So that's a negative problem over there. If you are taking class 2 as your positive class, then the errors may be class 1 and class 2, which are your class 1 and class 3, which are the erroneous results. So similarly, you will get down basically 3 different confusion matrices over there coming down. Now for each of them, you can find out the accuracy, sensitivity, specificity, precision and F1 score according to the formulas which are listed over here. Now accuracy is an overall prediction, which is how much you are going to predict both the positive class and the negative class in a good way. But that's not always true. In some of the cases, we would be looking more interested towards the positive class. I want to be very accurate for positive class. For disease scenarios, obviously this rate is supposed to be close to 100, which means that my number of false negatives should actually be going down towards 0, which means if there is a patient who has a disease, I cannot tell that particular person that you are healthy to let him go away, because that's where there will be no check at any further point of time. The other one is about specificity, where you can have a lower score given the fact that what would happen is that you can call a lot of people as false positives, which is a patient does not have a disease but has been said to have a disease. Now in any ways, after the automated process, at any point of time, the patient is obviously going down to a doctor who is a human expert, and that human expert is going to find out at that point of time. So the chances of the cost associated with doing a error over here is much lower, but the cost associated with saying a diseased person that you are healthy is much higher, because the person is going to die. Over here at least that thing is not going to happen over there. So from there, so these are about sensitivity, specificity and precision. But the final thing which a lot of people are liking these days is about the F score, because it's sort of a harmonic mean between sensitivity and precision. So what this does is that you have a weightage towards the true positive cases, but you also take into account the false positive and the false negatives, and this comes down to achieving sort of a regularized score when you have imbalanced data present in your classes as well. Because although you are training with a biased and totally balanced data by doing augmentation on your data space, but then you don't have balanced data during your testing. So that's where you need to take care of it. So from there we come down to this final thing, which is called as receiver operating characteristic. Now what it does is that you would look at the two axes, one is a sensitivity, another is a specificity axis, and what typically we wanted to do in this particular curve was that the idea was that say you have a probability coming down and you can take a decision by thresholding the probability at a point of time. Now as you select this threshold, say from 0.1 till 0.9, you would be getting down different performances coming. Now you need to choose like which is my ideal performance coming down over there. Now if you are not able to understand as to which one to choose, a good way is basically trying to draw this sort of a plot and finding out the area under this one. Now the higher the area, the better is the resilience to wherever you are trying to threshold. So what would ideally happen is that if ideal case would be a plot which is somewhat like this, and that would mean that any point I choose to threshold, I would actually be getting an area which is close to 1, and that means that my predictions are independent, performance of my prediction is independent of where I am thresholding, and I am no more dependent on that one. So which classifies algorithms as being better or worse amongst each other. There is another benefit of using this one as well. If you are trying to choose an ideal threshold, then what you need to do is draw another 45-degree line over here, and wherever it crosses this particular line, you need to find out what is the possible value of threshold over there and just use that threshold, and that's going to give you the best F score coming up at all point of time. Now once you know all the metrics and everything, the last but not the least is how are you going to tell about all unknown scenarios. And the best way of doing it is actually to do a folded cross validation. Now how we do this is quite simple. So you are going to create non-overlapping sample sets. So say I have a 2 class problem, class 0 and class 1, and for class 0 I have some n0 number of samples, and class 1 I have n1 number of samples, and I say that I am going to use k number of folds. Now if I am doing this one, what I would do is that I am going to train with n0 plus n1 divided by k times k minus 1 number of samples, and I am going to test on the n0 plus n1 by k number of samples. Now under a constraint that you will actually have to create k number of bags for doing the same. Now what each bag means is that in each bag you will have n0 by k number of samples for class 0 and n1 by k number of samples for class 1, and also ensure that there are no samples which overlap between bags, which means two different bags are not going to consider the same number of samples. That's what's going to again introduce some sort of a variance, some sort of a bias into your system. So you cannot share between them. Now what this is going to ensure is that at any point of time, at any fold, there will be a group of samples which have not been used for training the system at any point of time, and you are going to test on them. So this is going to ensure that after doing a sort of a round robin method of testing, so you start with fold 1 where you use set 1 in order to test and all the sets from 2 to k for training it. Then in fold 2 you are going to use set 2 for testing, and for training you are going to use set 1 and set number 3 to k for training it. So you are sort of doing a round robin over here, and if you take a complete loop over there, you would after some point of time find out that you have a sort of circle in which you are able to find out what is the total variance which your system might be having. So there would obviously be certain sets over there which will be biased towards a particular class and the other one towards another different class. So you will be seeing a trade-off between the accuracies which you can achieve. Now the best algorithm is that one which has the minimum amount of variance across all the folds and can give you the best performance. So this is what you are going to look at, the total performance in the wild for your method. From there the lecture ends, and I basically come down to a take home message which I have. So you can read for more details into this two texts from where most of the materials for making these slides were taken down, and with that I come to an end, and thank you.